All right, so I've got this differential equation up here corresponding to an undamped harmonic oscillator, because there's no y prime here, with a forcing function of cosine of 1.9t. So I want to find the general solution and then draw a representative solution curve. I'm generally going to ask you for a representative solution curve, and that's why in the last example, I wasn't super concerned that your initial condition was exactly right, because we used a particular initial condition to figure out what the period of the beats was and how many rapid oscillations there would be in each beat. Once we know that, that's the same for all of the solution curves. Okay? So I don't necessarily need to draw that particular solution. I know that information is true for any solution curve. But the amplitude of the beats and exactly where we start in the beat, whether we're starting at a high point or a low point or a midpoint or partway up in a sine function, that's going to vary a good bit based on the initial condition. Okay, so let's take a look. I know my solution is going to be the sum of a solution to the associated homogeneous equation and a particular solution. So the associated homogeneous equation is y double prime plus 4y equals 0. The characteristic equation is s squared plus 4 equals 0. So the roots of that are plus or minus 2i. Okay. That means y tilde, a complex solution, would be e to the 2it. E to the negative 2it would be another complex solution. But I know I just need to pick one, because one complex solution gives me two real solutions, because this is just cosine of 2t plus I times sine of 2t. That's the real part, that's the imaginary part. Y sub h is just an arbitrary linear combination of those. I'm still going to have to add my particular solution, but that right there is my y sub h. Okay. You'll notice that's a sum of some cosines and some sines of 2t. So the angular frequency of that natural response is 2. That's very close to the angular frequency of that forcing function, which I'm anticipating is going to be the angular frequency of the forced response, so I can expect there to be some beating. By the way, what this beating actually refers to, if I had a pitchfork here and another pitchfork here and they were slightly out of tune, that would be unpleasant. Kind of like receiving a beating. So we experience that when two things are close to being in sync but a little bit off, we experience this beating. We would experience a change in the volume of that dissonance that we would be experiencing. Okay. All right. Excellent. So I need to find my particular solution. So of course what I'm going to do is complexify the equation. So I'm going to recycle that y tilde and use that to represent an unknown function that's a solution to the complexified equation. And that would be e to the 1.9 times I times t. Notice this is the real part of that. So I'm going to try to guess that a particular solution to the complex equation is a copies of e to the 1.9 times I times t. My particular solution to the real equation is just going to be the real part then of that complex equation. Now I might remember from last time and be pretty sure I know what this is. Okay, I'm pretty sure it's going to be 1 over 4 minus 1.9 squared. So that's this angular frequency squared minus that angular frequency squared, copies of cosine of 1.9 t. I'm going to just confirm that. If you do enough of these that you accidentally memorize that result, I'm okay with that, but I would not try to memorize that result. It's relatively quick to derive, because yp tilde prime would just be 1.9i a e to the 1.9i t. So yp tilde double prime, I'm bringing down another 1.9i. So I'm going to get 1.9 squared, and you'll notice I'm just being lazy and calling that 1.9 squared, times I squared, which is negative 1. So I get negative 1.9 squared, a e to the 1.9 it. So if I plug this in, yp tilde double prime plus 4yp tilde has to equal e to the 1.9 it. So this is negative 1.9 squared times a e to the 1.9 it plus 4a e to the 1.9 it has to equal e to the 1.9 it. I'm going to factor out an a and an e to the 1.9 it. That is multiplied, it looks like, by 4 minus 1.9 squared. And this has to equal 1 copy of e to the 1.9 it. That's going to work if 4 minus 1.9 squared times a is equal to 1. So a will equal 1 over 4 minus 1.9 squared. So it's just the difference in the squares of the angular frequency of the natural response and the angular frequency of the forced response. Okay, now that means that yp tilde is 1 over 4 minus 1.9 squared times e to the 1.9 it. That's 1 over 4 minus 1.9 squared times cosine 1.9t plus I sine 1.9t. And I can see this is real, and of course that distributes through to it, so I did remember correctly that that's going to be my particular solution. Now, as I said, the angular frequency of that forced response is pretty close to the angular frequency of that response. So I want to now draw a representative solution curve. So I want to figure out what the beats look like and then how many rapid oscillations to put in the beats. So the three things I need are the amplitude of the beat, the period of a beat, and the number of rapid oscillations per beat. Now remember, the amplitude is just going to be the sum of the amplitude here plus the amplitude here, because the high point of the beats are when these two functions are really in sync, so they're hitting their highs together and they're hitting their lows together. Now the amplitude here is just the square root of a squared plus b squared, because remember, I can write that as c copies of cosine 2t minus phi. For some numbers, c and phi, but I get c by calculating the hypotenuse of this triangle. Okay, so it's going to be the square root of a squared plus b squared, plus I can see, oops, let me clear some space. The amplitude here is 1 over 4 minus 1.9 squared. So you'll notice the amplitude is determined by these numbers, which are determined in turn by the initial condition. So that's going to vary. Okay. Now, for the period and the rapid oscillations, I find it helpful to just create my little table of values. So I'm going to list the number, the associated period, and the associated frequency, which is just the reciprocal of the period. And alpha is just the average of these two numbers. So that would be 2 plus 1.9 all divided by 2. Now I'm just going to get this to be a slightly nicer number. That's 20 tenths plus 19 tenths. So that's 39 tenths divided by 2 would be 39 twentieths. Beta, on the other hand, is going to be this number minus this number divided by 2. So 1.9 minus 2 over 2. So that's negative 1/20 divided by 2. Negative 1/10 divided by 2 is negative 1/20. That's negative, but the absolute value of 1/20 is what's going to show up in calculating the associated period and the associated frequency. So a period is just 2 pi, the original period for sine and cosine, divided by this number. So that's going to be 2 pi times 20/39. That's going to be 40 over 39. Okay. Here I'm going to take the absolute value of that. Okay. 2 pi divided by that is 2 pi times 20. I dropped a pi, sorry. 40 pi over 39. Okay. 2 pi divided by 1/20 is just going to be 40 pi. So the associated frequency is 39 over 40 pi and 1 over 40 pi. Now there are a couple of ways to remember this. One is the beats are much longer than the rapid oscillations. So I'm looking for which period is bigger. This one is bigger than this one. Okay. The other is that the rapid oscillations have a much bigger frequency. So which is bigger here? This is much bigger. Okay. So we've now got pretty much what we need. So I can say, okay, if I were to draw a beat, there's just the sine curve that determines a beat. The period for that is 40 pi. I'm going to go ahead and draw in the mirror image of that. My rapid oscillations need to occur here in the middle of this. Okay. The amplitude, we said, was the square root of a squared plus b squared plus 1 over 4 minus 1.9 squared. I'm okay if you can remember that it's the sum of those amplitudes. I'm not concerned that you simplify 1 over 4 minus 1.9 squared. This would be the opposite of that, of course. So those are my highs and my lows. And now, if I look at the frequencies, this is 39 times as big as this. So I need 39 rapid oscillations in this beat. Holy cow. Okay, I'm going to just write in 39 rapid oscillations per beat. Please write it down and don't make me count how many you're trying to draw, but let's just try it just for fun. So if I'm doing 39, that's going to be 19 and a half. Now, when I'm not assuming any particular initial condition, I'm going to just start here at 0 and draw a sine so I'm on my way up. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Ugh, this is tough. I didn't give myself enough room. I'm going to start over just because I can do this and I'm going to be stubborn about it. Okay, so I just need to make them a little bit tighter. Okay, I know I want to be at about 10 rapid oscillations when I'm halfway done. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13, 14, 15, 16, 17, 18, 19 and a half. Holy cow, that's crowded. Okay, now I'm just going to totally estimate here. Now, if you have a smaller number of rapid oscillations besides 39 per beat, if you had 4 per beat or something like that, I would expect you to actually draw that so that I could count the 4 per beat. And I will try to rig the problem so that that's actually doable. You should be more rapid. Okay. But kind of interesting to see how that plays out. Okay.